Okay, it's almost 12:01. This is Michael McClellan, L-3 Electronics and Electrics. Thank you so much, everybody, for coming and supporting us, and hope you're getting something out of these webinars. Today, we're very lucky to have our own John Levine presenting. John has at least 40 years of experience in the electrical and industrial communications world. John is
older than I
am. Yeah, John's got 130 years of experience. So with that, before I hand it off to John, just a couple housekeeping issues. This is a GoToWebinar, so your phones are muted, and there is a box to your right in the toolbox where you can ask questions or use the chat box or raise your hand. There's lots of different ways you can signal us that you have a question or want to have a discussion. So, and with that, I'm going to turn it over to John.
Cool. Good morning, good afternoon, or good evening, depending on where you're located. We've had people on these webinars from California to New York. And we also have this recorded, so some people are actually watching in the middle of the night. I'm John Levine of Levine Electronics and Electric. We're a manufacturer's representative organization that covers Georgia, Alabama, Florida, Mississippi, Tennessee, and Arkansas. We've got two divisions, a control division and a power division. So we can help you in that arena. Our philosophy is to give back to the industry. So to make it safer and better for all, we've got 3 team members that are actually officers of IEEE IAS, and we've also got 3 people that are on the IEEE Pulp and Paper Subcommittee. I want to thank Michael McClellan, who's been running these webinars. We've done one almost every day, and you can find these recordings in our resources page of our website. Today's presentation is on fundamentals of industrial and utility communication. It's actually one of my favorites. It's full of items that can make your life easier when it gets involved with communications issues. So hang on to your hat, because I'm going to cover a ton of material in the next hour and going very fast. So with that, of course, my first question is, are you frustrated and having trouble? Are you ever frustrated because you can't get on the network or you can't get on the web? You know, it always mystifies me how a person with an Apple computer can send an email when you're using Microsoft Outlook. And how do I talk to these protective relays? All these questions will be answered and hopefully more, because this is all part of communications. Before I begin, I just want to give you a personal insight. I thought when this IoT, Information of Things, or a lot of people call it IIoT, I thought it was a bunch of malarkey and never would take off. But let me tell you, I was totally wrong. It is unbelievable what we can do with this Information of Things. One of our suppliers is GE Multilin. They've actually added electrical signature analysis to motors now, and you can get all this data back. I can see eccentricity in a motor. I can see a soft foot. I can see bearing misalignment. So there's a ton of stuff that this IoT has given us now, and all of this gets back to, you got to have communications. We have another supplier, Danfoss, that's got some ESA type functions. They've got vibration built into it, load profiles, so I can look at horsepower and see if a pump's got clogged up and it's not pumping, or a blade's broken. So it's really amazing where it's gone. What I'm going to cover today is I've broken it into 4 different categories. I'll cover some basics, which I'm going to go very quickly on, Ethernet protocols, and HMI. So let's get into the basics. In the basics, I'm going to have an introduction, briefly talk about serial parallel, parity, network standard, and the OSI model. So what do we have here? When we talk communications, you're going to have a transmitter, you're going to have a receiver. And there's different ways these devices talk to each other. Simplex is what we used to have with old printers, and the data would just simply go one direction. Then you have half duplex. What that is is each device can talk to each other, but only one person can talk at the same time. And then full duplex is when you have 6 people in a room and all 6 of them are talking and everybody's talking and listening at the same time. So it can actually, the signal can go both ways simultaneously. Let's talk a little bit about formatting. Bit is either a 1 or a 0, so that's just a 1 digit. Then you have a byte, which is considered 8 bits. You have what's called a word. That could be 2 bytes, 4 bytes, or 8 bytes. There's a thing called ASCII, and what that is that stands for American Standard Code for Information Exchange. And they've come up with standard nomenclatures to represent, say, letters. So A may be 0010 1000. Then you also have what's called hexadecimal. That's based on 16. Well, once I get over 10 in a decimal system, I run out of characters. So now we add the characters A to F. So when you get into something like a Modbus address, they may say the address may be something like 030D, which is in this case says a differential. So once I get past 10, I just go D, E, and F. So you'll see that, and that tells me immediately it's a hexadecimal format. In parallel with the old printers, remember we had that 25-pin connector. They actually used 2 logic levels, 0 and -12. And all this is media, as I'm talking about right now. These are not protocols. A lot of people talk about like RS-485 as being a protocol. That is not a protocol. Serial was really taken over for what used to be the parallel connection. It's kind of interesting. You'll have what a start bit, you have a stop bit, and we actually look at the time. The timer goes from the start to what the middle time should be of the signal, and we can actually use that to make sure that signal goes through. We also have parity. You may hear the terminology even parity or odd parity or no parity. In this case, I've got 3, this to me appears to be odd parity. So I've got 3 characters since this is a 0. If it was even parity, I'd put a 1 here. That would make it even parity. You also have baud rate. That's how fast the data is moving. You may hear 19 or 9600 bits per second. Sometimes you may see, now the new stuff's going 115 bits per second, or even faster when we get to USBs. So they have what's called different physical layers. 3 common ones are 232, 485, and USBs. And as I mentioned earlier, these are not protocols. These are physical layers. So let's see how the industries define these. So 232 actually uses a logic 1 from -3 to 25 volts and a logic 0 from 3 volts to 25 volts. So you've got a 50-volt differential. And this slew rate is how fast it can go from -25 to +25 or vice versa. Then DTE stands for data terminal equipment, and DC is data communications. There's a lot of terminologies I'm going to come and cover in this. So you've got a transmitter and a receiver. RS-232 can only go a distance of about 15 meters or 45 feet. That's what it's limited to because of this voltage level. RS-45 is really kind of cool because in RS-45, you've got a transmitter and receiver, but here what we do is the logic 1 goes from -1.5 volts to 6 volts, and a logic 0 is from 1.5 to 6 plus 6 volts. But what they did in 485 is I can go up to 3,000 feet. And the way they do that is we actually have RS-45 actually floats. So this one may be at 100 volts, and this is 106 volts. So I'm only looking at the differential between these 2 lines, and that's how 485 works, because the conductors are actually floating, which is kind of cool. Now what happens is everything's starting to go to USBs. USB 2, we had like the Type A and the Type B. With USB 3, you now see a connector like this, and I'll show this better in the next slide. As a side note, I went ahead and threw Apple's Lightning on here, which is a slightly different topology. But what was interesting to me is USB 2, we went to about a half a gig, 480 megabytes. With USB 3, it is screaming. It's going 4.8 gigabytes per second. USB type A and B have 4 wires in them. 2 are for voltage, so we have plus or minus 5 volts, and then a twisted pair to carry the white data. And that, just so you know, on USB type A or B, you could actually have 5 volts up to a half an amp. That's the way it was designed. So now we get into USB. Here I'm showing the type A and the type B. It was a 4-wire system how it's set up. Some of you may remember the mini A's and mini B's, and micro A and micro B. These have kind of gone by the wayside. Everything now has gone to USB type 3s. And what's interesting in USB type 3 is instead of 4 wires, we now have 9 wires. So we've got all the transmission data here and then the voltage levels here. My old phone actually had this type connector, which I never realized was actually a USB type B type connector. A lot of us have seen the USB type 3s, but it's got 9 pins versus this that had 4. And I personally have never seen a USB type B in this kind of configuration, which is similar to the type Bs for the 1 and 2, but it's obviously got 9 pins in it, which I thought was interesting. I had run across my old laptop, actually had a connector for this, and I never understood what it was. It actually is an IEEE standard 1394, and a lot of cameras had this kind of connection. That was actually developed by Apple, Sony, and TI, Texas Instruments. This standard, actually, and this is years ago, was able to talk at 100, 200, or 400 megabits. And then FireWire S3200, it was 3.2 megabits. So it was far and away ahead of what we did with Microsoft and standard USB connectors. Okay, now I'm going to go into what networks are and give you some terminology. Most people know a LAN stands for local area network. So that's what we've got if we have a LAN. You also can get into what's called a WAN. So here's where I'm going over the internet. And later on in my presentation, I'll talk about coming into my office. I have a WAN address that I convert to a LAN. So this is how we can convert and go between different networks. And this is where we get into firewalls. You may hear of a MAN, that's metropolitan. BBN is backbone networks. GAN is a global area network. So there's a bunch of different terminologies that we get into. Let's talk a little bit about topologies. Here's 5 common topologies. The first is a bus topology. Something like DeviceNet that Alan Bradley uses actually uses a bus topology, and you just literally clamp on to this bus where you want to get that communications. Modbus is similar to this, but Modbus, I daisy chain into the first one, then I daisy chain in the next one, next one. A ring topology is kind of interesting because the data can go either this way around the ring or this way around the ring. The advantage of this is if the ring gets broken in one spot, you can get data still back to the network. A star topology is probably what most of you have in your house. You've got a router in the center, and that goes to all the different devices. An extended star is similar to a star, but now I may have a second router or switch somewhere else, and that goes out. And then probably the most reliable of all the networks is considered a mesh. And in a mesh, literally, I've got every point talking to every other point. And I'm going to talk about some other topologies a little bit later. Another protocol that's come out very recently is called PRP, which stands for Parallel Redundant Protocol. In Parallel Redundant Protocol, what we've got is the devices can have 2 completely separate IP addresses that go to them. So if one network gets bogged down for whatever reason, I could come through this other network and get to the device. I'm going to talk about an offshoot of this called HRS, which is really a version of PRP in a future slide. So that's a new protocol that we're starting to see a lot more of. Here's some of the different standards. You've got ANSI, IEEE, IEEE that affect communication standard. One thing that's interesting, I attended a Georgia Tech Relay Conference one year, and what's happened is all of a sudden we're using communications for turning devices on and off, protective relays. So all of a sudden we had to have ANSI numbers to represent all these different symbols. And ANSI number 16 has really been adopted to pick it up, and you can find all this in IEEE C37-2. So if you've got a firewall, you need a nomenclature for that. So that's F. You have networks and managed switches. You've got routers, switches. And so all these things now have ANSI numbers. So the consultants that are on the line may want to get access to some of these ANSIs. I've got a copy of this paper on our website at l3-com/resources. So you can find this 2008 proposed C37.2, which has come into effect. Okay, now we talk about the OSI, and I'm going to cover this very briefly because it always bored me to death. But the reality is this was actually developed back in 1978 of how are we going to have all this stuff talk on an internet and communicate. So you find out there's different layers. My next slide actually talks about it better. So the physical layer controls the connection between devices networked. This is where all the 232.45 or USB, all that's controlled by the physical connection. Then you have a data link level, networking level, and as I get further in this presentation, when you start Googling stuff, they'll actually tell you what level of the OSI its information is connected on. Everybody's heard of IP, like TCP/IP. That's level 3. The TCP is at level 4. Then you get session presentations and applications. Those use level 5, 6, and 7. Just to let you know how it's set up. Okay, I'm now going to go into Ethernet. I'll give you an introduction, some other things, switches and hub, and talk about fibers. So Ethernet is a high-speed LAN standard where you can have devices talk to each other. What happens is devices now have IP addresses, and that's really their name. So you may hear something like 192.168.10-5. That's an IP address. In relays, we also have slaves addresses. So in this case, this relay has a slave address. If I'm talking to a relay out in the field, then I may want to give it a static IP address. Something like your computer, when it gets on the network, your IT provider will have DHCP. So they actually assign a dynamic IP address to the relay. The problem is, if I can't talk to that relay, then I've got a real issue. So that's why we tend to have static IP addresses in it. Recently, I saw a presentation by a device that Siemens was doing, and they actually can give their devices, and Danfoss drives can actually do this too, where you could actually have the PLC assign a DHCP. And they do that by knowing the MAC addresses and some other factors. So that's what it actually is going. If you want to connect to a device, there's two things you're going to, especially if you're talking serial, you're going to need to know the baud rate, and you're going to have to know the IP address, the slave address, okay, or the IP address. With Ethernet, you can go 100 meters or 328 feet. And sometimes it's talking 10 megabits, 100 megabits, or 1,000. Okay? It's one thing that people are starting to get into. They needed faster communications. Cat5 is good for 100 megabits. So all of a sudden, if I'm talking a gigabit, they need to go what's called a Cat6 cable or a Cat6A, Cat 6 can go 250 megahertz or 500 megahertz on 6A. Just so you know, 6 is not necessarily better than 5, since obviously we get into a lot of industrial applications and utility applications. What we find is to get 6 and 6A, you got to have less capacitance in the system, which means it's more susceptible possibly to noise. So if you're going to use these cables, I recommend you use a shielded cable to help protect it. But sometimes 5 is better than 6. The next thing I want to cover is PoE. That's power over Ethernet, which is kind of cool. Standard Ethernet uses 4 of the 8 conductors. So I'm using 1, 2, 3, and 6 for transmitting and receiving signals. Okay, and this is done at 48 volts. So just like we had, just like we had 25 plus 25, the 6 volt floating. With Ethernet, it uses a 48 volt signal. What's happening now is they've added, since I had these 4 extra wires, I can add 48 to 4, 5, 7, and 8. So why does that slide keep changing on me? That's so rude. So like our telephone in our office, we have a PoE system. We actually get the power for the phone system over from the Ethernet switch. So you can buy an Ethernet switch that has the power built into it. So that's kind of nice. Or you may have at the plug. Okay, my presentation wants me to go to the next slide, so I'll go to it. Now we're going to talk about fiber. With fiber, what you've got to know is a power budget. The transmitter have a certain amount of power they can generate. So if I'm going a short distance, I may have to have a different transmitter than if I'm going a very long distance. Then you have attenuation, and there's actually attenuation in the fiber. So that's how much that signal drops. And then I have a receiver, and it's got a certain amount of sensitivity that it can receive. So, you know, we've had situations where people bought the wrong transmitter and it actually could burn out the receiver. So you need to do the analysis, and there's formulas for calculating it. Pretty easy to know what you've got there. There's 2 types of fiber. There's single and multi-mode fiber. Multi-mode fiber to me is kind of cool because I may have this signal go straight this way, or I may have the signal bouncing back and forth. The problem is I need both these signals to get back to here at the same spot. So the way they do that in multi-mode fiber is they actually dope the signal in the center. So this slot wire here, since it's doped, actually takes longer to get from here to here than if it went this way. In single mode fiber, what we do is we actually have like mirrors and lenses, and they constantly refocus that signal back to the center. So that's how it works for single mode fiber. In multi-mode fiber, there's typically 2 standards, 62.5 or 50 micrometers. In single mode, typically it's only a 8 micrometer signal. Single mode fiber tends to be more expensive than multi-mode fiber. And you've got to see how it's set up and make sure your devices are designed to handle that. Here's some connectors you'll see. Probably the 2 most popular I see is ST and LC. I don't see that much SC fiber. Some of the devices actually can use an SFP, which stands for small form factor pluggable. These are a little more expensive, but they're really nice. And some of the devices we sell actually, you can get this as an option. Here, what you can do if you don't know what you need is you can actually buy them, and if I have the wrong connector, I can just unplug this and plug a different type connector in there. So those are SFPs. So that's actually a little more expensive, but they're really nice to give you flexibility of what you need for your application. I'm going to give you an example where fiber really is nice. GE Multilin has a product called the brick or hard fiber. And what they traditionally did in the substation was I need to get all the CT connections, all the PT connections, all the IO connections from the breaker back into the switch house. So what they would do is you've got this mass of terminals where I bring all those CTs, PTs, and IO connections here. Then they had to run it through a trench and get back to all these connections are typically set up on a wall in the switchyard, and then they've got to connect them to the relay. Well, one great example of fiber is I can run all those right in the switchgear to what's called a hard brick. And this uses a connector that uses a process bus called IEEE 61850 process bus. Now I just run one fiber connection. In this case, we actually run 4 identical fibers back through this cable. And I can eliminate about 33 connections there. Then I eliminate about 40 connections in the cable, eliminate all those connections to terminals by running it into a terminator box. A lot of times I don't even use that. And then I can run those 4 signals here. I could run one to a feeder relay. I could run to a bus differential. So I can run it to all these different devices and eliminate huge labor savings. Especially if you get into repetitive type applications, you can have huge savings of wire by going with fiber. Great solution. Okay, think I'm running on schedule here. Amazing. Now let's talk about hubs and switches. Okay, a hub is pretty much you won't see anymore, but just for your edification, hubs, what happened was a signal came in and it got retransmitted to all devices. And you'd hear the word collisions and the network would automatically start slowing down. So now today what we use is mainly switches, and switches, what we can do is when that signal comes in, we just have it go where it needs to go. So this eliminates a lot of collisions. And there's 2 types of switches. There's an unmanaged switch or a managed switch. And an unmanaged, there's a little configuration. You plug it in and you go. A managed switch has all kind of additional features where you can control the network, which is kind of nice. And I'll talk about that in the next slide. So you may hear SNMP. So that stands for Simple Network Managed Protocol. So that's a set of protocols for managing and solving network problems and planning for network growth. IGMP is Internet Group Management Protocol for broadcast messages. I'm sure most of you have heard of called a VLAN. I can have literally 2 separate LANs going through the same switch, and the 2 cannot talk to each other. So that's what we use a VLAN for. QoS is quality of service. That's very, very important. In, say, a protective relay application, if I send a trip signal out, I need all those other devices to trip immediately. I don't want it to wait in its queue. I want it to be prioritized. So you can actually set prioritization levels from 1 to 8. So I can make it where that bypasses and immediately goes out. If I'm just collecting information, that may be priority 1. If I have a trip function, I can make that priority 8. So we can actually prioritize packets. In rapid spanning tree protocol helps with topography and mistakes. Today with Ethernet, most of your computers, I think I missed it when I did that slide. We used to have what we had to call crossover cables. So if I had 2 computers talking to each other, I had to make sure I change my wiring on one end. Now the computers can actually automatically sense. But with rapid spanning tree protocol, it can automatically adjust and do that kind of functionality we couldn't do before. Here's some typical additional switches for the Plant 4. So here's when this has got some Cat RJ45 connectors as well as some fibers. GE Multilin's gone to the Reason switches, which is a division they owned. I can have gigabyte ports. I can have fiber. And you can mix and match them. Here I'm showing daisy chained all these devices going into a 232 and coming out as far as 45, or excuse me, Ethernet. So you can actually have media converters, and I'll talk more about that in another slide. One methodology we use for connection with switches, here I've got what's called a ring topology. So this way the signal can go this way around the ring or this way around the ring. If it gets broken, it automatically can go the other way. And these take about 5 milliseconds for that signal to go between the switches. Okay? Next, a version of PRP is called HRS. And what I do in this is I actually have that signal going both directions simultaneously. And then each relay, depending on which signal it receives first, it accepts it, and then it automatically just ignores the second one. So that's how HRS works in a nutshell. Okay? Okay. So now let's talk about wireless. In wireless, this is really where I see the future. Products will be designed with wireless. There's 3 common frequencies, 900, 2400, and 5800. The faster the speed is, the less distance it goes. So that's why we see a lot more 9 megahertz, because it'll go a longer distance. 5800, obviously it's talking faster, but it cannot go as far. Okay? One thing you can get on your phone, and I've actually used this on applications, is a Wi-Fi analyzer. This is actually the Wi-Fi at my house. So I've actually got 3 different Wi-Fi access points. And what you can see is they all have different signal strengths. So you can actually load a Wi-Fi analyzer on your telephone, and it'll show you this signal strength. Now the magic number here is minus 60 dBs. If I've got more than 60 dBs, and more means, because these are negative numbers, going this direction is stronger, then you've got an extremely good signal. When I get down to the 70s and 80s, these are not good signal strengths. I actually had a test application where one of our customers had some transformers outdoors, and they wanted to know if they could use their existing Wi-Fi, and we could set up some Wi-Fi meters, because I've got some meters that'll accept Wi-Fi. So I pulled this little program out, saw we had about 65 decibels, and told them, it'd be good if we could get some kind of another Wi-Fi transmitter closer to those transformers outdoors. So this is a great tool you can use to analyze your Wi-Fi network. When you get into Wi-Fi, there's all kind of different signal strengths and speeds, and the cost is proportional. So like here's one that'll go up to a megabits. This one only goes to 115. You can get licensed and unlicensed wireless devices. The advantage of a license is you're the one that controls that network. Unlicensed, you could have somebody else that possibly could be on that same network. If I actually go back a slide, you actually see on a different frequencies, there's 14 channels. So even though these are all on the same networks, there's different channels at that 900 megahertz. So you want to make sure you set up your network so they're all indifferent and don't overlap from that standpoint. Okay. A router is designed to forward packets across the network. This occurs at layer 3. Remember, I was talking about different layers? That's that internet protocol, the IP of the OSS 7-layer model. So that came right out of Wikipedia. And one thing that I think is kind of cool is Wikipedia and Linux are actually volunteer organizations. They're open source. They're very popular. There's a ton of information, yet it's all done on a free basis, which I think is kind of interesting. Some other computer network devices we have what's called a gateway. A gateway is designed so I can have two networks talking to each other. So, I get asked a lot where a multi-lane relay may talk Modbus, but they'll say, I need to talk BACnet. So what we'll do is we'll have a gateway that can actually convert Modbus to BACnet. So that's what we call a gateway. And in the device itself, you just set up A phase current in Modbus is this register, A phase current in DeviceNet is this. A bridge is designed to connect multiple networks together. So I may need to have network 192.168.3.x talk to 10.10.3.4. So you can have a bridge to have two networks talk together. And a repeater just amplifies a signal. So, a lot of times in your house, you have weak signal in one place. You could use a repeater to get a stronger signal down the road, the other end of your house. Some other terms I've already talked about. PRP, that stands for Parallel Redundant Protocols, where I can have two separate LANs go into the same device. Bandwidth is how fast it transfers that data. A server is a computer program running to serve the request of clients. It's interesting when I get into DNP3 further, they actually use the terminology backwards. But typically, think of a server, it's serving the request of the clients, and your computer is a client. VPN stands for Virtual Private Network, and RSGP, which I mentioned before, was Rapid Spanning Tree Protocol. And that determines the message it'll take between two nodes. And we'll show this further later down, but you're going to the cloud, into networks, into Google. Well, the Google location you may go to is in California. It may go through Texas to get to that signal, or it may go through New York. So Rapid Spanning Tree decides how we're going to get from point A to point B. And it actually, if you've got a gigabit's worth of data, it may take packets, part of them go one direction and part go another route, but they all come back together at the other end. It's really wild when you really get into it, how it's all done. Some other terms, IRIG-B is a time code we'll use in protective relays. It's only got an accuracy of about 10 milliseconds. SNTP, this is what all your computers have. Have you ever noticed that all our computers gets the time from a clock? It's actually at port 23 is what they usually use. But I like to put this into all our relays, but you got to go to a 1E option to get it. But this is a very simple way for me to get all the protective relays to have the same clock time. So if you want to get that specified, just make sure you have a device that can go SNTP. PTP is Precision Time Protocol. This is when I start using GPS clocks to actually do the time sync. And this gets down to sub-microseconds. So now if I have like two relays and I want to get the oscillography files out of them, I want to make sure those times are synced almost precisely. So you get into that. QoS is quality of service. We talked about that, and that's where I can prioritize messages. And one thing a lot of people don't realize is they'll say, I want a GPS clock. Well, you can get a GPS clock that just uses the US standard. GE Multilin actually sells GPS clocks. There's actually two global satellite positioning services that run around the globe. GPS is the US one, but GLONASS is the global navigation satellite that's used from Russia. So we've actually got some relays that are up in the Arctic Circle, and there we chose to get a clock, GPS clocks, that had both of these. So if it loses a GPS signal, it can go to the GLONASS and pick up the signal there. So that's kind of cool. Other terms, proxy, computer network service allowing clients to make indirect connections to other networks So you'll hear of a proxy server. Firewalls I'm going to cover in more detail, but this is a piece of hardware or software that can either prevent or allow something going through to a network. And a lot of times when we can't talk, it's because somebody's got that firewall blocked. And the way you get through a firewall is through a computer port. This may be a hardware situation. So something like COM3 is a hardware port. Or you're here 502. That's a situation where I use a computer port to talk to multi-LAN relays. That's typically used for Modbus. Port 80 and 81 are used a lot of times for when you get into the internet communications. And sometimes they use a computer port that's software. That's like the 502 or 8081. All right. When you're talking to devices, one of the great tools you've got is called the device manager. If I'm talking to relays, I need to know what port that USB is plugged into. So here I'm actually using my USB to RS-45 converter, and I can see it's called a prolific USB to serial converter, and it's on COM3. So when I go to talk to that relay, I can use the device net manager to find out what port I'm talking on. I've had situations where this thing comes out and it says it's at port 17. Well, I may have a device that doesn't go to 17. You can actually right-click on this and force this COM port to go to the properties and change it to a different port if that port's not in use. So that's a great tool to keep in your bag of tricks. So this is how firewalls are set up. So you can set up applications. You say what port's it going to start at, what port's it going to end. So this is on the WAN side. Okay, so it comes in on my WAN. I'm using TCP protocol, and it goes to this IP address. Next, I'm going to show you a bunch of relays because this really shows it a little better. I've got a bunch of relays in our office in Atlanta, and I've got a T35, a V90 M60s, SVM 745s, 489s. So I've got it where customers can come in through our WAN IP, which happens to be 172, 165, 187, 153. So if you go to that WAN address and go to one of these ports, I automatically redirect you to our LAN, and then I've got these relays on the LAN set up at certain IP addresses. I'm using port 502 on the LAN side, and not only that, but you may need to know, for like a multi-LAN relay, what the slave address is. So you can come in to the WAN IP, that wire firewall port, the slave address, and it automatically redirects you to that relay. And if you want to play with our relays, give me a call. I'll make sure you can get through and talk to it. We've also got some relays like got an EPM 7000 or 9900 that are actually meters. They've got built-in web pages. I can actually have you go right through our WAN address, go right to this port, and that'll take you right to the WAN address. So if you want to play, you could actually put this into your browser, and it should take you right to these relays, and you can play with them. We also offer serial to Ethernet converters. So this is a great way. Here, I'm showing it right here. So these devices were connected serially. They come in, and then I can go through an Ethernet converter and connect to that. And I'll show you this on the next slide. So one thing, if you're talking, let's say Modbus, you're supposed to have a terminating resistor and capacitor. Just for your FYI, I've had people just put the resistor. It actually bogged down the network because they didn't have the capacitor. So you should have on each end a resistor and capacitor, and these are the values. So that goes into the serial. Then I can either have fiber or RJ45 connector and have that go up to the LAN. Okay, so how do you connect a device to the network? If you've got static IPs on these relays, I've got to make sure my computer is on the same network. So in this case, I've got a relay that may be at 394.244.12. So I need to make sure I put my computer on that same network to talk to it. So what I'm going to do is go to Properties, and then I come to IP4 and go to Internet Properties, go to Protocols, and then you may have to change your IP from a DHCP to a static to be able to talk to the relays. So you've got to make sure they're on the same network. Now, we used to use IPv4. You may have heard we're going now to IPv6. IPv6 went from these 4 characters, now it's to 8 characters. And they're using hexadecimal, so you can now get into that. So because we ran out of IP addresses, that's the new format that is set up in all computers. If you want to check your IP address, I'm going to show you what we used to call them DOS commands. You can type in CMD, that gets you to a command prompt. And through the command prompt, I'll pull up this, and you can click it, and you can actually check. And here's a bunch of commands that I love using. The first is all called ipconfig. So with ipconfig, what that's going to do is that's going to give me all the different connections. And you'll find there's not just one connection. You're going to have a wireless. You may have a local network. You may have a virtual private network connection. So that'll give you all those connections. Okay? So my wireless connection happened to be 192.168.1.20. My same computer was connected to the local LAN through 394.244.1. People sometimes don't realize, but through an Ethernet port, I could be talking 4 different protocols, talking 4 different network connections, and all these devices have different connections. If I need to get out of the command prompt, just type in the word exit, and that'll get you out. So ipconfig is a great command to remember. If a lot of people will say you can't get on the network, so what do? So they tell you to reboot your computer. What you're basically doing when you reboot your computer is releasing and renewing that IP configuration. If you want to try it, you can go to that command prompt and just type ipconfig release, and then ipconfig renew, and that'll automatically release and renew the IP, and it may be a lot quicker than having to reboot your computer. If you don't know all the commands with ipconfig or any of these commands, you can hit -H, or like here I put a -T, put -H, and that'll bring up the help. I can type the command ipconfig all. That'll not only give me my IP addresses, but all the MAC addresses. And what a MAC address is that's a way to identify the computer, and every manufacturer, when they have IP addresses, automatically have a MAC address. And typically the first 2 octets of that is assigned to a manufacturer. So like Multilin's got it where you can have Discover, and because they know their MAC address of all their devices starts off a certain way, they can find all the MAC addresses and automatically tell you what the IP addresses are because of that. And that's kind of what Siemens and some of the other manufacturers do. One of my favorite commands is ping. And if you do -T, instead of doing the ping 4 times, it'll do it continuously. So what I actually do a lot of times with ping is if I'm having trouble connecting, I'll run the ping and then I'll start reconfiguring to see if plugging in different things will help me find it. Trace route I'll show in another slide. That's kind of cool. If you can't get to a certain website, you can see where it gets stuck. So it'll give you all the steps from you and that server you're trying to talk to, which is a cool command. Netstat is one that's displays the network connections. For transmission control protocols, shows the routing table and another network stuff, which is kind of interesting. Exit I talked about before to get out of it. If you're in the command prompt,
You can hit F3, goes to the previous, or the way I like to do it is just go up arrow. So if I went from IP config to ping, and now I need to get back, I can just hit the up arrow to get to it. So here I'm showing a couple of different things. So I can hit ping and put in the IP address, and it'll automatically ping it. A lot of people don't know, but if I want to ping Google, I can type in ping Google. And with what's called a DNS server, it actually takes Google, and it knows that Google, one of their addresses, is 64.233.167.99. And obviously Google has thousands of IP addresses. So it automatically takes a DNS server, converts it, and this is what happens when you Google a name on through your Chrome or Internet Explorer or Firefox. It converts it to that IP address, to the DNS, and then it can find it that way. Just as a side note, there's 13 master DNS servers, and they're labeled A to J. So when you put in a new name, that DNS servers, it actually filters through the whole internet, and that's how that works. So that's kind of an interesting side note. Here I'm showing traceroute as an example. So here it started at I was tracing the route to Google, and it'll give me up to 30 hops. So it went to my gateway, then it went out to this 73, then it went in Marietta to a Comcast server. It bounced to 4 different servers at Comcast. Then it went to an AT&T server. Then it went to a Quest server. Okay. And then it finally ended up, and it had one timeout in the process, it ended up at that server at Google. Okay. So traceroute will actually trace, and you can see where it gets stuck in the process. The next thing I want to talk about is blacklist, whitelist, and gray list. A blacklist is something that blocks it. A whitelist allows it through. And a gray list, it'll block it the first time, but the second time it'll allow it through. So that's how those work. Here's some useful internet sites, DNS stuff. You can find if a website's getting blocked or who owns it. I use SPEAKEASY.net a lot of times to find my speed and see how that is. SpinRite can check for leaks in your firewalls. If you have an IP address and want to know whose it is, there's a site for that. What is my IP? Give you your WAN IP. And Wireshark's a great tool for troubleshooting. So here's speed check, SPEAKEASY, so I can see my speeds. If you're less than 10 megabits, you need to fix it because that's too slow. And typically, I care more about download. Upload you don't really care about because you're not seeing it, but you need to be at least at 5 megabits. Wireshark, here I was actually trying to see if these goose messages were going through, which is an IEEE 61850. I was able to see that. Okay, I'm running behind schedule now. I'm going to quickly go over some different protocols. And every protocol's got advantages and disadvantages. Modbus is a great protocol for data. It's terrible for communications. The reason for that is it's a half duplex. But what happens is you have a master and a slave. The master sends a request to the first slave. The first slave gives the answer. Then it sends a question to the second slave. Second slave comes back. If you're using Modbus, I do not recommend you put more than 6 devices in serial. Technically, you can have up to 32, but if you do, it'll be extremely slow. The way Modbus works is you have an address, a hex address, and the manufacturers pre-decide what that is. So 0236 is hottest bearing RTD. So you say, tell me what's at 0236. He goes out and gets it and comes back. The next one is Modbus Plus. And Modbus was designed by Modicon. So that's where the name comes from. This is a proprietary protocol. It also uses 485. But what it does is it uses a pure token. So instead of just having one master, it can pass the token and anybody can be the master. It goes faster, it goes up to megabits, and I can go 1,800 feet without repeaters. Next is DNP. This was developed by GE Harris. This is the protocol that most utilities use. Here we have a client and a server. Remember I said earlier, they do it backwards. They call the client is the computer, which to me is asking for the request, and the server is the device. They also sometimes call it master slave. It's kind of cool because it can just tell you pull for changes. So instead of getting all that data like Modbus did, you can just change for data. You can also set it up so once an hour it says, give me what your A-phase current is. It can only provide change values and you can prioritize. So that's a cool protocol for those things. And the way it does is it's got 4 layers. It's asking you for an object, a variation, a function code, and qualifier. So in this case, the object is a static analog input. It's 16-bit integer, request to read, single point access. So it uses those 4 levels, similar to what Alan Bradley's protocol is with DeviceNet and Ethernet IP, which is my next slide. So in Ethernet IP, that's based on CAN protocol, and that's Open Device Net Vendor Association. There's a 24-volt topology. They've got different baud rates. You can have up to 64 nodes. And once again, it's got object classes, instance, and attributes. And so here you have a overload object. So that's the object. It's got class code instances, and these are the different attributes. So I may want full load amps as an attribute. Profibus is what Siemens tends to use. Profibus is a serial. Profinet is the Ethernet version. So there's different flavors of Profibus. You've got a process bus, decentralized periphery, field bus, process automation. So they've got different things depending on if you want more data acquisition or control. And by the way, Ethernet IP is a better at control than for data. Profibus to me is similar to how Modbus works because I send a command and get a response. And the way they do it is similar. There's different layers of Profibus depending on how much information you can get out. So they got 3 different layers of how much data. Like you got to go to DPV2 if I want to get clock synchronization. To me, it's similar to Modbus, and they have a register, and they give you that value. IEC 61850, this is a protocol we use a lot with protective relays. It's based on Goose, and we can have transmit and receive. The way it works is it's kind of like a newspaper. You have a publisher and a subscriber. So the publisher publishes it, and you can decide who's going to receive the messages. I can have it set up where literally everybody can talk to everybody else. Different applications, I can use it for a main-time main. Instead of using 14 wires going between all the devices, I just connect 1 fiber and I'm done. It's actually more reliable than putting in wires because within 2 milliseconds, I'll know if something's failed. I can do load shedding schemes, voting protection, transfer trip bus, a lot of great applications of it. Heart's kind of interesting because it uses a 420 milliamp signal. So you say, how do I get zeros and ones? Well, what they do is they just put a 0 or 1 above or below where the milliamp output is. So that's kind of how Heart works with communications. BACnet stands for Building Automation and Control. So this is adopted by ASHRAE, ANSI, and ISO. And this uses who has that, who am I, who has, I was, different kind of commands like that for the communication protocol. And if you have somebody needs a gateway, you can get gateways. EtherCAT's the last one I'm going to talk about. And what's cool about it is it actually starts decoding the packet. It's super, super fast. This is the protocol that I believe is in most automobiles. It actually starts decoding it before it's even received the whole packet. So it does it on the fly. So that's kind of neat. There's protocol converters. So I could go from like the ByteNet to Modbus or Profibus to Modbus. And you can have that go both ways. There's also some universal gateways. So these devices actually could take 12 different protocols, bring them all in, and convert them all to one protocol. They got web pages built in and other devices. Real quickly, let me go with some of the HMI stuff. So this is where SCADA comes from. So this is, I can have all that information come back to a central point. The RTUs are the remote terminal units. That's feeding back that data. This is super easy in today's world to get this information. I can have plug and play, so I can get all this information on this. I can have dashboards, so I can see all the data, all the metering, everything coming back. Here's an example we did for one customer. And they've got pumping stations from Houston to New Jersey. And literally what we've done with that is we can see the green means it's closed. This means it's open. If they have an issue, the engineer or the technician can literally analyze it. Some of these are unmanned stations. So while the engineer or tech is analyzing, the guys going out to the station, they found they saved 3 to 4 hours in downtime and troubleshooting, because now when the guy gets to the station, the engineer or tech can say, go to breaker number 3 and see and change this. And we've got all this data which we never had before. So it's fantastic from that standpoint, because we've all on a network. To change it is super easy. This is a super low cost package. So if somebody wants to crawl before they run, we can actually do that. You can have enunciators in there. You can have Comtrade and waveforms. So here's a trending report. So if I want to get the data every hour, what's going on, I can actually see that. I can see Comtrade files. So if there's a problem, and one thing I like doing with Comtrade files is don't only trigger what on certain conditions, but I like to do cross oscillography. So if any device has an oscillography, I want to grab all of them, because sometimes it's not what tripped, but what didn't trip. So we can see why a device didn't trip, which is kind of nice. Okay. OPC stands for is a foundation. So you'll hear OPC DDE. So this is how they set up how these devices are all going to talk and treat each other. And here's the DDE server. So that's data exchange. So something like Microsoft Excel has a DDE server. You could actually set up Excel to grab all those registers out of a protective relay and put them onto the DDE server. And here, actually, this is the case I actually used multi-lens integrator, and we had relays. We actually had them talking to a Schneider PLC, and then the Schneider PLC was talking to a Rockwell HMI. And by using this integrator and an OpenC DDE server, I had all three of them easily talking and communicating with each other, which is a very cool application. So here's my source of information. Wikipedia, Profibus, ODBA. GE Multilin has a resource page. So a lot of what I stole came from these ICOM and UCOM presentations. And you can find, they've broken them down from an hour presentation, hour or 3 hours, to short segments if you want to go to that and find it. Also, I will have this on our resource pages. So if you go into the communications section, I don't have the video yet. It's because I got to wait till I finish this presentation. But I've actually got 2 versions of it. One's just the PDF file, and here it is with notes. If you look under the handout section, you can go ahead, and I've uploaded both of these to that, so you can download those. Should have told you that first if you wanted to make notes on it early. And that is my presentation. I'm only 4 minutes late, which for me is absolutely amazing on this. Michael, I'm now going to let you ask the polling questions. If anybody has a question, you can go ahead and put it into the questions, and I'll answer them after Mike does the polls.
Now, while we're doing that, let's go over some of the questions. Here's a good question.
Where's my hair?
Where is your hair? Yes.
Yes, where's my hair? I can see the questions, Michael. Where's my hair? I lost it when I was 16 years old. Communication problem. We have lost audio. That's very funny. I can't help you there. Just in the future, if you lose the audio, I suggest you just dial in, because there's no ground conductor in RS-485. I've noticed, yeah, they don't ground the conductors. They do ground the shield. And you only want to ground the shield at one end on RS-485. Okay. You're 60 seconds up. You want to go to the second question, Michael?
Well, way to go, Carlin.
And I'm sure Billy would love it. We actually, for those that in Georgia, Alabama, and Florida, ASHRAE now has a requirement. Georgia's adopted ASHRAE 90.1. Alabama's adopted some of it, and I'm not sure about Florida. But we actually have a solution to offer you, and we have a spec we can give you to meet ASHRAE 90.1. And Billy Sanders heads up that activity for us.
And there will be a webinar on that shortly.
The question was, can you talk about duplex connectors? Not sure what you mean by that question. I mean, I cannot. IRIG-B was, the question was 10 milliseconds or 10 microseconds. I believe IRIG-B is 10 milliseconds. I'll have to go back and check that, but I'm pretty sure that's what it. And then the next question was, is CAN like Modbus? No, CAN is dramatically different than Modbus in the way they're set up. What is the name of the phone app you mentioned used for analyzing a Wi-Fi system? The name of it is Wi-Fi Analyzer is the name of the application. Looks like you got the next question up, Michael, which is, would you like us to contact you about a lunch and learn at your facility?